This video is going to be all about decoding a CAN message, taking the raw ones and zeros that are extracted from the CAN high and CAN low electrical signals that you might have probed and using this to identify information like the message ID or the value of the data that's being communicated or whether the message was communicated without any errors. CAN messages are really just a string of these logical bits and follow a standard and predictable format. We're going to start with a full CAN message and work our way through all of the different fields of information until we have a good understanding of what every bit in this message is doing. So to start, I'll put an entire CAN message up here on the screen for us. This entire message is sometimes called a CAN frame, and you'll be able to see on the screen that we have the CAN high signal, the CAN low signal, and the voltage delta between the two, as well as the decoded dominant 0 and recessive 1 bits that correspond to this delta signal. The vast majority of CAN messages contain exactly 13 fields of information. That is, 13 separate things are communicated through this bit stream. And to take a look at the very first of these, we're going to have to zoom right into the start. Once the CAN bus is free, any node on the network can signal its intention to speak by asserting a so-called start of frame bit. This bit is dominant by convention. In other words, the node pulls the bus to dominant away from its resting recessive state to communicate that it would like to speak. Next, that node will communicate an 11-bit message identifier. This identifier is obviously a binary representation, and because you have 11 bits to play with, there are about 2,000 unique identifiers that you can play with in this field. After broadcasting the 11 bits corresponding to message identifier, the very next bit to be broadcast is a so-called remote transmission request or RTR bit. The RTR bit communicates whether this message is a so-called data frame or a remote frame. Data frames are the most common. They're what we use almost all of the time in CAN. It's where we want to communicate some information. To communicate a data frame, we place a 0 dominant bit in this RTR slot. But there are also types of messages called remote frames, which place a 1 recessive in this slot. Remote frames are a special type of message that don't have any data associated with them. They're basically an empty CAN message that only has an ID. Remote frames exist so that you can poll other ECUs for information. You might have ECU A send a remote frame with the ID of the thing that it would like some information about, and ECU B might be programmed to listen for remote frames, and when it receives one, reply with that information. The truth is that remote frames are pretty rarely used in CAN bus, and consequently the RTR bit almost always carries a dominant 0. The very next bit in the transmission is called the identifier extension bit, or IDE. In very, very large CAN bus networks, it's possible that you may want to communicate more than the 2,000 or so unique messages that you can get out of an 11-bit identifier. If and when this happens, you can place a recessive 1 in the IDE slot to unlock an additional identifier field immediately afterwards. This additional field allows you to have many, many more CAN messages on your network. For the most part though, and particularly within new teams, we only really deal with standard 11-bit identifiers, which means that we ordinarily place a dominant 0 in this slot. The next bit that's broadcast is a so-called reserved bit. And exactly as the name suggests, this bit has been reserved by the standard for future use. It may be the case that a later revision to the CAN standard places some value on this bit, does something interesting with this bit, but for now it's largely ignored, and we place a dominant 0 in this bit by convention. We'll have to pan the message across now to see the rest of it, but immediately following the reserve bit comes a 4-bit field called the data length code, or DLC. CAN messages are able to carry data payloads anywhere from 0 to 8 bytes long, and the transmitter can decide how long of a message it wants to send, depending on how many variables it might want to pack into one message or how much resolution it would like for each of those variables. The only requirements are that you must send an integer number of bytes, you can't send parts of a byte, and the number of bytes you specify within the data length code must agree with the subsequent size of the data that you send in the CAN message. For instance, the data length code shown here is 0001, which is the binary representation of the number 1. In other words, we're expecting to see a data payload in this message which is exactly 1 byte or 8 bits long. And serendipitously, the data payload is what comes immediately after the DLC in a CAN message. The data field is a variable length field. In other words, for some CAN messages, it can be as small as 8 bits long, and for others, it can be as long as 64 bits. Again, depending on what was specified in the data length code. This data payload is 8 bits long and reads 00010101, which corresponds to the decimal number 21. There's often a trade-off between the length of a data payload in a CAN message and the resolution of the variable you may wish to broadcast. In this case, and assuming that the entire 8-bit data payload was being used to broadcast one variable, we'd have a resolution of numbers starting at 0 and ending at 255. In other words, this 21 represents something which is about 10% of the way through that resolution. Of course, you can get more resolution by using more bytes of information in this data payload. If you have 2 bytes, you get way more resolution than 1, for example, and it's very, very common to use 2 bytes for the vast majority of things you might want to transmit. We have to pan across again now before we can see the next field because it is 15 bits long. That field is called the CRC, or cyclic redundancy check. A little bit like a checksum that tells you whether a credit card number is valid, the CRC tells a receiver whether the data that they've received is valid. It's calculated on the transmitter end and is broadcast after the data payload, the CRC being a function of the data that was sent before, and the same calculation is performed on the data payload at the receiver's end, which compares it to the transmitted CRC value. The type of CRC that's used in CAN will allow the receiver to identify up to 5 randomly distributed bit failures, but this is pretty rare owing to the robustness of the standard. For the most part, the CAN network will work or it won't. It's very rare for data to become corrupted along the way. We have to pan across now again to see the next bit, which is a CRC delimiter, a recessive one that's placed by convention after a CRC to communicate its ending. The next bit along is called the acknowledgement bit, or ACK. And this bit allows a transmitter to know whether any receivers on the network have heard its message. When sending a message, a transmitter will assert that the ACK bit is recessive. Receivers on the bus who have heard the message and calculated the CRC and identified that everything is all good will respond by pulling this bit dominant. Remember from way back in the electrical signals video that if 2 nodes try to assert a different state on the bus, the dominant assertions dominate. And transmitters rely on this fact to know whether their message has been received. They assert that the bit should be recessive and they listen to see whether it's pulled dominant by somebody else. If it is, it means that their message has been received okay. There are 2 important things you need to know about the acknowledgement bit. The first is that the transmitter has no way of knowing whether all of the nodes on the bus have heard its message. It only has a way of knowing that at least one has heard its message, because while all nodes that have heard the message will try to pull the bus dominant, as long as at least one does, the bus will become dominant. The transmitter has no way of knowing whether 2 or 3 or 4 or 10 nodes have heard its message. It can only know that at least one has. The second thing you should know is that if the transmitter doesn't see that its recessive assertion has been overwritten by a dominant, it will enter an error state. This usually happens if you only have one CAN node on a bus. Say you're trying to diagnose one node and you've got your oscilloscope out, but you haven't got it connected to any others. Because that node never receives an acknowledgement, it tries to resend for a short period of time before it reverts to sending these things called error frames. Again, this is pretty rare provided that you've wired up your CAN network correctly, so don't worry too much about it. Much like the CRC, there is a delimiter bit placed after the acknowledgement called the ACK delimiter, and by convention, a recessive 1 is transmitted in this bit. Finally, to signal that we've reached the end of the CAN message, a transmitter will send 7 consecutive recessive 1s in what's called the end of frame field. This long stream of recessive 1s indicates to all other nodes on the network that the bus is about to become free. And if any other nodes have messages queued up, ready to go, they can start to prepare to send them. Following the end of a message, the bus needs to be free for at least 3 bits. This is called the interframe spacing, or IFS. And these 3 bits in combination with the 7-bit end of frame usually provides enough time for any other node on the network who is about to send a message to gear up and get ready to do so. So to sum up, let's zoom back out and look at all of those again. Our message begins with a start of frame bit which pulls the bus dominant away from its resting recessive state. This is followed by an 11-bit message identifier that tells receivers what information they're about to receive. A 1-bit RTR field that's used to communicate whether this message is carrying data or requesting data, but again, for the most part is usually only used to communicate that we're carrying data. A 1-bit identifier extension field that's used to communicate whether we're dealing with an 11-bit identifier or a far longer one. Again, for most of our purposes, we'll be dealing with an 11-bit one. A single reserve bit that's been stashed away in the CAN standard for later use. A 4-bit data length code that tells the receiver how much data is inside the payload of this CAN message. The payload itself, which is as long as the data length code has specified. A 15-bit cyclic redundancy check that allows the receiver to determine the fidelity of the information it's received. A delimiter for this redundancy check. A single acknowledgement bit that's used by receivers to tell transmitters that their message has been received. A single delimiter bit for this acknowledgement. 7 recessive bits to signify the end of a frame. And a further at least 3 recessive bits to space between CAN frames, between CAN messages. And that's an entire CAN message. Now, I don't expect you to remember any of this off by heart. The wiki page associated with this video has a list of all of these fields and what they mean and how much space they take up and whether they're dominant or recessive by convention. You should go and check that one out if you ever have any questions. To sum up, I need to talk about one more thing though, which I've neglected in the discussions of this video. It's called bit stuffing. Now, the CAN standard is self-synchronizing. In other words, all of the nodes on the bus operate on the same kind of regimented, rigid bit schedule. And CAN nodes manage to do this without communicating what the time is to each other or without having some external clock kind of source of truth. The way that they do this is by looking at changes in the state of the bus. Every time a bit is broadcast, CAN nodes can adjust their internal clocks to make sure that they're in time. Of course, what can happen is if you have a long string of repeated bits, you don't have any changes in the bus state, and it's possible for some drift in this timing to occur. To solve this problem, the CAN standard enforces the use of stuff bits. In CAN, if 5 consecutive bits are broadcast of the same sign, in other words, if 5 dominant bits are broadcast or if 5 recessive bits are broadcast, they must immediately be followed with a so-called stuff bit of opposite sign. In other words, if you send 5 dominant bits in a row, you must immediately follow these with a so-called stuff bit, which is recessive. For instance, this bit stream over here, which has 5 consecutive dominant bits, should be modified to this bit stream over here, which introduces a stuff recessive bit. And this rule must be rigidly followed no matter what comes afterwards. This bit stream over here, which has 5 consecutive dominant bits followed by a recessive bit, still requires a stuff bit because there were 5 consecutive dominant bits. It should look like this over here. And kind of confusingly, stuff bits also count as bits for the purpose of bit stuffing. In other words, this bit stream over here, which gets modified to this bit stream over here because it's been bit stuffed, now requires another stuff bit because you end up with 5 dominant bits in a row. It should look like this. Again, this is something you probably don't need to worry about most of the time. If you only ever interact with the CAN bus through software, say on a microcontroller or with a piece of off-the-shelf hardware or a computer, well, the CAN controller of the transmitter and the CAN controller of the receiver automatically handle this. You don't have to worry. You don't have to build it into your messages. But if you're ever diagnosing a CAN bus or interrogating a CAN bus with an oscilloscope by hand, you need to remember that if you ever see 5 consecutive bits, delete the one that comes immediately afterward. It was a stuff bit. And that wraps up our discussions about the CAN message format. Again, you should check out the wiki page associated with this video. It has all of this information summarized with expandables. It should be pretty easy to go through.